Three things in graph theory. When we have a graph, let's say I draw a graph like this, and then some random edges between the vertices. I didn't name the vertices, I didn't name the edges, but that's not important. So here we have a graph, and each vertex has its order. That means how many edges are connected to it. So this vertex has order. Okay, I'll write the order in a list for all the vertices. There are 4 vertices, so we'll have 4 numbers in that list. So this one has order 3, this one has order 2, this one has order 3, this one has order 2. Now, I have a list of the orders of those vertices, and there's something called a non-increasing degree order, or non-increasing degree sequence, and that basically means is we have a sequence that lists these numbers but in a decreasing manner, and if they're repeated once, well, that's why we don't really call it decreasing, we call it non-increasing. So if they're repeated once, for example 3, 3, they're next to each other in that list. So if I want to write this in that decreasing / non-increasing order, I will write 3, 3, 2, 2. So I took all the orders of those individual vertices and I listed them from the highest to the lowest, and if they're the same, they're more with the same order, I just put them next to each other, and after that I put those that are again, for example, repeated but lower. So 3, 3, 2, 2, decreasing but non-increasing, because here one by one we don't have any decrease always. Alright, so that's that. It's called the non-increasing degree sequence, where we take the degrees of all the vertices and list them in such a way. And now we had a graph, and I created a list, and I created a sequence from that graph. So I found out the orders, and I made a sequence. But we can also go the other way. We can have a sequence, some sequence of integers, that behind them we first of all know this will be 5 vertices because 5 numbers, and individual orders for those vertices, being those numbers that they are. So we can go the other way, not from a graph to the sequence, but from a sequence to a graph. So either you know that that sequence can represent a graph's vertex orders, or and you can just draw it, or you don't really know. And if you don't know, then you can check it, but you don't have to draw the graph imagining it. You can use an algorithm for that. So that's what we'll be doing. So I delete this, and now we're not dealing with a graph out of which we made a sequence, but we deal with sequences, and they're already listed in that way. They're decreasing, or at least non-increasing. So we see 4, 3, 3, 2, 1, decreasing in general. The same here, 3 times 2 and 1. What it means is, again, 5 vertices here, 2 have order 3, 1 has order 2, 1, 1, and 1 has order 4 here correspondingly. So these are 2 different sequences. This is a graph, this is a graph. Well, the question is it a graph or not? So if that sequence indeed represents a graph, it is called graphical. So that's what we're looking for. So this algorithm I'll be using is basically telling us, is this sequence representing a graph? Can there be a graph with such orders of individual vertices? So we see, can there be a graph exactly here with 5 vertices where the orders are these numbers for each of them? And to answer that question, we'll use this algorithm. So first of all, there is some general information we can refer to. For example, if we add the degrees together should be even. Then the graph is constructible from that sequence. If it's not, then if the addition of all the vertices orders is odd, then it's not possible. So let's see, 7, 10, 12, 13. So actually it should not be possible. But I can still apply that algorithm to show how the algorithm is used with already knowing that it won't end up. And depending on the algorithm's outcome, we can again verify what was already said. Sometimes one can quickly find out that it cannot be a graphical sequence, meaning a graph cannot be constructed with this information, because if the addition of the degrees is odd, it's not possible. So let's apply the algorithm to this one first, and then we do the second practice problem. So 4, 3, 3, 2, 1. I'll just write the numbers like here, and then the algorithm is as follows. Remove and it's already sorted. That's important to have it sorted. All right. So always the next step is following when the numbers are sorted from the highest to the lowest. So the algorithm is as follows. Remove the first highest number. So remove 4. And then because the first highest number was 4, subtract from 4 of the next elements 1. So you always subtract 1 from the next elements. But from how many depends on the number that was removed. Because 4 was removed, we subtract from the following 4. So if there were 10, only from the following 4 we will subtract. Here it turns out that there's only 4, so from all of them we will subtract 1. So instead of this, we will have 2, 2, 1, 0. So that's what we have now. And now we can reiterate this process. Now, why are we doing this algorithm this way? It's because each of those transformed new sequences we make out of this, again, are decreasing or at least non-increasing locally. So in general, non-increasing, they go down in the value with those numbers. And there's both sides implicit relation between the initial sequence and these transformed ones with lower orders. Because with these lower order ones, it's faster perhaps for one to verify if it's possible to construct such a graph. And if this new one can be a graph, then the initial one must also be a graph. So that's the idea. So we are making it simpler and we can look at each of them. Can it be a graph or not? And if one does not want to just use this simpler, simplified one and try to construct a graph from this one to see if the initial one was 1, then one can just keep on doing this process until one gets basically to 1s and 0s. So let's reiterate, although now it might already be easier to see if it's possible. We can still reiterate. So again, remove the first one, which here will be 2, and subtract from how many that first one is, 1s from the next element. So I remove 2, being the first one, so from 2 of the next ones, I subtract 1. So I remove 2, and then this one will be 1, this one will be 0, this one is 0. So we have 1, 0, 0. So what that means is, there is one vertex, basically, there is only one vertex of degree 1, which is not possible because the degree depends on connected edges. And there's just one vertex, it must have degree 0 because the edge cannot connect it to anywhere. So that's the point. So this is basically a contradiction that we came to, and thereby we verify that initial knowledge already that is not possible with this algorithm. So 4, 4, 2, 1, it's not graphical. A graph cannot be made out of this sequence. And then again, we can do the same thing for the second sequence. So this sequence we'll now use 3, 2, 2, 2, 1. So I'll write it out again. And again, the same algorithm. Remove the first number, and from what the value of the first number is, remove from that amount of the next elements the value 1. So I remove the 3 and I subtract 1 from the next 3 because I removed the 3. So 1, 1, 1, 1. We just get 1s here actually. And there is a general thing that one can note. The rule is, first of all, always, if the addition is odd, it cannot be graphical, cannot be a graph. If addition of all of them. Now, if their addition is even, there is that possibility. We will verify, but there is that possibility. And if all of them are 1s and it's even, it's already clear from experience that it will be possible, it will be a graph. Because with an even number of degree 1, we can always do this sort of graph. 1 connected to another one, so 2, which both have degree 1 because they are connected by one edge, and then another one. And we can make as many as we want. So as long as we have even number of 1s in that newly reiterated sequence, transform sequence, then we can always draw something like this. If we have 2 1s, we will just have one of these. 4 1s, this will be the graph. 6 1s, 8 1s, 3 of these, 4 of these. 10 1s, 5 of these. But I can still continue with that idea, kind of, right? I don't have to refer to this knowledge here and say, conclude it, yes, now we already know it's graphical, yes, this represents a graph, we already know. But I can just continue with the algorithm to practice it. So I remove the first number and I subtract 1 from how many, what is the value of the removed number. So I subtract 1 from only 1 of the following ones. So I remove the first one and I subtract 1 from the next one, so I have 0, 1, 1. And now, of course, the 0 I kind of ignore. What I can say is I remove the 0 now and I first subtract 1 from 0 of the next ones, or I can just ignore the 0. And then again I reiterate it and I basically get in the end to a 0. So again, I remove a 1 and subtract 1 from the next one. So I have 0 left. So eventually I get to a 0. So if I get to a 0, meaning we're concluded without having to draw any graphs. Okay, on the way we had new sequences, and if those were drawable as a graph, then the initial one, with which we started, is also graphical, meaning it can be a sequence made into a graph. And another way, we don't have to draw any graphs on the way, but if in the end it's 0, then yes, that sequence in the beginning was graphical. So that's verified as yes, the sequence was gonna be a graph.